Lesson 13.1 is going to help us get into some probability. We're going to actually learn how to count. And just to get us started, take a look here at the top of the page. If A is a set with n elements, there are 2 to the n subsets. So think of a set almost as a box or a bag with items in it. It does not have to be numbers. It could be letters or objects such as triangles, squares, whatever you'd like. But it's a collection of objects. We could say that there are n of them, n elements. You might wonder, wow, 2 to the n subsets. How is that going to work out? Let's take a look at a couple examples. Let's say we have the set of 1 and 7. There are 2 elements. N would equal 2. So it says list all possible subsets. Well, according to what we have just seen, there should be 2 to the second, which is 4 subsets. So here's what we're getting at. We've got this collection of items. We've got the number 1. We've got the number 7. A subset could be the set just containing 1. It could be the set just containing 7. It could be the set itself, which is 1 and 7. That's always going to be a subset as well, the set itself. Well, right now you can see we've got 1, 2, 3 subsets. You might wonder what our last subset would be. Well, that would be the empty set. The empty set means that none of those were selected. So this is what we're really looking at. Let's say that we've got a set with the numbers 1 and 7. Someone could just select a 1. That's our first subset. Or just a 7. They perhaps could select both. That would be the 1 and the 7. Or maybe they'd select none. So that would be our 4 subsets. You'll always have the set itself and the empty set as part of your subsets. Well, let's say that we take a look at number 2. We have the set A, capital A, having lowercase letters A, B, and C. Here, I hope you would agree that n would equal 3. There are 3 elements, 3 items in between those brackets. And the question is, how many subsets? Well, according to our little theorem, we should have 2 to the n. 2 to the third is 8. So we should have 8 subsets. Now, like we just said earlier, you're always going to have the set itself and also the empty set as your subsets. Here are 2 of them. You might think, well, my goodness, what are the others? Well, we could have the singleton A, a singleton of B, a singleton of C. What else could we have? Well, we could select A and B together, or perhaps we would have selected A and C together, or perhaps we'd have B and C. And if you think about that, these are the only 8 ways, if you count up all of these subsets, we've got 8 of them now, that we could have proper subsets. Well, let's take a look at another problem. Let's say that given that you have 100 students, 35 take a math class, 52 take a computer class, 18 take both. How many are in a math or a computer class? And then B, how many are in neither? Well, let's draw ourselves a little Venn diagram. Venn diagrams are wonderful. They're used not just in math, they're used all over the place, really. But we could have this circle right here indicating those who take math. We could have this circle over here for computers. We'll just say COMP. So it says you've got 100 students. 35 take a math class, 52 take computers, but my goodness, would you look at this, 18 take both. Well, I'm going to start off by writing 18 right here in the middle. There are 18 students who are simultaneously taking a math class and computers. There are 35 students who are taking math, and we already know that 18 of them happen to also be in computers. That means 35 minus 18, which would be 17. 17 students are taking math all alone. Well, what else? We also know that 52 students are taking computers. Of those 52, 18 are also taking a math class. Well, we can subtract and very quickly see that there would be 34 students who would just be taking a computer class without taking the math class. The 34 of them plus the 18 who are also taking the math class would add up to 52. So for part A, they're saying how many of these students are in math or computer science. Well, if you're in math or computer science, you'd be in math alone, perhaps taking math and computer science, plus those who are just taking the computers. So it's 17 plus 18. We know that's 35. 35 plus 34 is going to be 69. So there are 69 students enrolled in math or computers. For part B, how many are in neither? Well, if there's 69 students in this circle, but there are 100 students total, I'll take 100 minus 69 and very quickly come up with 31. So that means there'd be 31 students outside of these circles who happen to be, in this group of 100 students. They just happen to not be taking math or computers. Okay, well, if A and B are finite sets, what our book will write, and I think we need to see this, the n, meaning the number of A union B, would equal the number in A plus the number in B minus the number in both. So this union right here would be the word or. This intersection right here would be the word and. So what we're seeing is, of course, we're seeing that if you want to find the number in set A or set B, add up set A, everyone in set A, add up everyone in set B, but then we have to subtract where they intersect. Here's why. Let's take a look at this Venn diagram that we had up above. Look, if A was the number of math students, and if we add up the number of math students, that's in yellow right here, and then if we said, hey, let's add up just students who are taking computers, well, that would be in green right over here. You can see when we do that, we've double counted the overlap. We've double counted the number of students in math and computer science, so we'd have to subtract them out. So that's why this theorem is going to hold true. Revisiting 3a from up above, if I wanted to say find the number who are in math or computers, well, my goodness, I could take the number in math plus the number in computers minus the number who are in both. And think about it. We'd have 35 plus 52, and then we'd minus 18. And if you work that out, you're going to find that you would get 69. So hopefully that's a nice alternate way to do it. Here's another issue we can deal with. What if A and B have no elements in common? In other words, There is no overlap whatsoever. If we drew the Venn diagram for A and B, A would be over here, B would be over here. No elements in common mean that there's no intersection. So what are we getting at? The number of A or B would just be the number of A plus the number in B. Obviously, the intersection itself is 0, and you could still use that formula. Last one, the counting principle. Well, if there are n ways to perform task A and m ways to perform task B, there are n times m ways to do both, to do A and B. So we'll finish up with this problem very quickly. Let's say that a restaurant offers the following choices for a meal. For an appetizer, you could either get a soup or a salad. For an entree, you could have chicken, beef, liver, or shrimp. And then for dessert, you'd have ice cream or cake. We're going to assume that one of these selections must be made each time. That you can't say, no thank you, I don't want one. So for this appetizer, there are 2 choices or 2 ways you can select an item. For the entree, we'd have 1, 2, 3, 4. 4 choices that you could make. 4 ways you could select that entree. And then finally, for dessert, there'd be 2 choices as well. Assuming that a choice is made for each of these stages of the meal, how many different meals can be ordered? Well, counting principle. 2 times 4 times 2. You could say there'd be 16 different meals that could be constructed from these choices. All right, well, for your homework, it's going to be a book assignment, page 854, 855, 7 through 31, the odds. We'll pick this up again next time, but best of luck to you.